Hello everyone. What I'd like to talk a little bit about today is the operation for making Lewis structures for molecules and for ions, polyatomic ions. So again, the topic is going to be Lewis structures, and we're going to get into this with respect to how this is modeling the electron configuration around atoms and ions. So, first of all, the Lewis structure represents the electrons. Those structures represents the electrons around an atom or an ion as only the valence electron. So this is going to represent the valence electrons. Now, just to make sure that we're discussing the same thing in terms of expressions and definitions, the valence electrons are the outermost electrons in the atom and represent typically the electrons that will be used for bonding. So let's take an example of a Lewis structure and go through the process of setting it up. If we take something like fluorine, for example, fluorine has a total of 9 electrons, and it has 9 protons. So the nuclear charge is exactly balanced with the electron charge. And if we go through this process and examine the structure, we find that if we write the electron configuration for fluorine, we get 1s2, 2s2, and that's 4, and then 2p5. Now, this is a complete set for the electron configuration of fluorine. If we now are going to be concerned only with the outer shell, we represent in Lewis structures only those with the highest principal quantum number, which in this case is 2. So you notice that we have a pair of electrons in the s sublevel. If we represent that as the one is spin up, the other is spin down. And in the p sublevel, we typically can represent 3 sets of p. So we have 1, 2, 3 spin up, and then 4, 5 for a total number of electrons. We have then 3 pairs and 1 lone electron surrounding the fluorine valence structure. So if we were to write this now with the structure represented by dots, what we would have would be fluorine, and we put a pair as a pair, and another pair here with respect to the configuration, finally a third pair, and now we have 1 lone electron. Now this is also equivalent to moving that lone electron and keeping the pairs anywhere around the symbol for fluorine. For example, it's just as valid to write something like this, and of course any other place, as long as you keep the pairs as pairs and the lone electron as a lone electron. Okay, so that is an example of the valence configuration for fluorine. Now we know that fluorine, like several other elements on the periodic table, is presented to us as a stable molecule which contains 2 fluorine atoms chemically bonded with a single bond. In other words, there are atoms that are sharing 2 electrons between them. And if we do this for fluorine, we can write the configuration. Of course, the general shorthand is to put F2, which is the shorthand for the fluorine molecule. If we write it out now with the configuration of the Lewis structure, we write a fluorine here, we put a pair of electrons, a pair of electrons, another pair of electrons, 1 electron here from this fluorine. Now we put in the other fluorine and we put the other electron next to it. So these 2 are the shared pairs, and then we have the other 3 pairs. So you notice that if we look at the structure, we actually have the fluorine in each case can be assigned an octet. So we could put, here's an octet for this one, and of course they're sharing it. So here is an overlap and an octet for the other one. So each of those fluorine atoms, now represented by this structure, shows an octet, or 4 pairs. Okay, this octet configuration is important for our study here, to continue the configuration of covalent and ionic compounds. This octet represents a stable structure for many compounds that we will encounter in this class. So for example, because chlorine is in the same family as fluorine, you'll have exactly the same configuration of pairs on the outside of the valence structure, and so Cl2 will look very much like F2. In fact, we can take a look at several other configurations. For instance, here is hydrogen fluorine as a gas, hydrogen fluoride as a gas. So if we were to write HF as a gas, its representation on this configuration would be the fact that hydrogen has 1 electron, that's it, and fluorine has 7. So again, here we go with the 3 pairs and the lone pair. Now we have an octet around fluorine, and notice that we have a pair of electrons around hydrogen. Now, this is akin to showing the structure electronically of helium, because helium has only a pair of electrons, and this makes the hydrogen electron configuration very much like helium. And by the way, the fluorine configuration is very much like the other noble gas, neon. And that's what a lot of these patterns are going to come out to be when represented as octets. You'll find that they are then looking at the electronic configuration of the noble gas elements. Okay, well now we can take a look at something else, very similar ideas. For instance, if we take the configuration in the Lewis structure for carbon, carbon is the structure that we see for 4, and if we write out the electron configuration for carbon, we get 1s2 and 2s2, right? And then 2p2, okay, which means it has 6 electrons for its 6 protons. And of course the outer shell looks like this, just the p's. So if we were to actually write carbon as a single atom, it would look like this, carbon, and it would have a pair of electrons here, and have a pair of electrons here. Well, that's far from an octet. So if we were to make something like carbon with 4 bonds that we typically see, what we'll have to do is find a way to make an octet with electrons around carbon and any other element that comes into the configuration of the molecule. So let's take an example. Let's take our fluorine again, which has 7 electrons around it. So if we put a fluorine here, and I'm just going to mark these with X's so that we can differentiate them for the moment, you notice that we could have an octet made if 1 electron came and bound between a fluorine and a carbon. Of course, that would leave 3 other electrons not bonded. If we repeat this process 3 more times, for a total of 4, if we put a total of 4 fluorines across the configuration of carbon, we would have something like this. We'd have a carbon, and here what we'll do is we'll put the fluorine around it. Okay, and there's 1. There's another carbon and another fluorine, and that gives us 2. And here's another carbon and another fluorine, and this gives us 3. And here we have the final carbon and the final fluorine configuration of electrons. And now you see that fluorine in each of those cases has an octet. I'll just surround one of them just so you can see. And carbon, by sharing 4 of its electrons with 4 different fluorines, all of a sudden you see that carbon now has an octet. So here we have carbon tetrafluoride, and by looking at the structure you can see that the configuration is as an octet for each one of those atoms inside the molecule. Okay, so now what I'd like to do is just give you some general concepts of how to formulate the Lewis structures for any of these configurations that we will be considering. So let's take a look at them. For example, we might take a look at something like phosphorus trifluoride, for example. So phosphorus trifluoride has a formula PF3. Now, when we look at these, what we see very quickly is we have one element that is by itself, so to speak, and another element that is in multiple steps in terms of its atoms. So one of the things to consider is to think of a way that you might arrange these. Well, one of the obvious ways to arrange it is to put the one that's by itself in the center and the multiples around it. Another way to consider this is the most electronegative elements typically tend to be on the outside. Those are the ones that hang on to electrons most tightly. Fluorine, for example, oxygen, nitrogen, chlorine. So in this case, if we make an arrangement of these, we might consider the fluorine to be on the outside and then have the phosphorus on the inside. So we might put P and an F over here and an F over here and an F over here. So that gives us a configuration in space as how these things might be arranged. Now that we have a spatial arrangement, we might consider the next step. So we'll put this as step 1, and we'll call this a spatial arrangement. Spatial arrangement. Okay, now the next thing we might do is consider the electrons. This is strictly the valence electrons. And for this, we might consider setting up the valence structure of each of these. So let's count the number of valence electrons. So we might put step 2. So we'll call this valence electrons. What are the valence electrons? And they are going to represent the way this structure can form its covalent or ionic bonds. In this case, we have 3 fluorines. So 3 fluorines is the same as saying that we have a set of valence electrons of 3 times 7 or 21 valence electrons from the fluorine. What about the phosphorus? Well, phosphorus is in the same group as nitrogen, and so the valence electrons that we're going to consider for the phosphorus are 5. So we have 5 valence electrons for the phosphorus. So we have 5 valence electrons for the phosphorus, and we only have one set of those 5. So that's going to give us a total of 5 electrons here. It gives us a total of 26 electrons. There we go. Now the 26 electrons can be arranged around this configuration, but before we do too much, first thing we want to do is make single bonds between each of the 2 elements that are going to be making up the structure here. So this case, or atom types, if you will. In this case, if we put the fluorine on the outside and the phosphorus on the inside, we could have phosphorus here with a pair of electrons representing a bond to a fluorine here. We could do the same thing on this side to another fluorine, and we could do the same thing to this side to another fluorine. Okay, so we've used up 2, 4, 6 electrons. We have 20 electrons to go. With 20 electrons to go, we would fill the outside electrons first. So if we do that for the fluorine, what happens is we get a total of these electrons as pairs. So we have 3 sets of 8s, or 3 times 8 is 24 electrons. So far we've used up 24 electrons. You notice that every fluorine already has an octet. However, the phosphorus in the center still does not have an octet. By putting in another pair, which now makes it 26 electrons, which is exactly what we need, we now have an octet around the complete structure. Now, I put the phosphorus electrons at the bottom. Many times you'll see them in the books. They'll look like this with the phosphorus lone pair at the top, and the others configured around the structure as so. And of course, they're all octets now, so there is a configuration of 4 pairs around every atom in this structure. Now, sometimes this configuration is expressed a little bit more shorthand if we present this as phosphorus with a single bond to fluorine here, a single bond to fluorine here, and a single bond to fluorine here, noting that each single bond represents a pair of electrons. And you can see mixed situations where there's another pair. And again, here we have the same Lewis dot structure that is representing phosphorus trifluoride in all 3 cases. So, again, what did we do on the last step? In the last step here, what we did is we took and arranged each, let me say step 3, arranged all the electrons, arranged electrons to form octets with the central atom. Well, first to form single bonds. With the central atom. And step 4, we might call that. Step 4, what we're doing is we're putting the remaining electrons, as lone pairs, or as multiple bonds, as we'll see in this next example. So here we've made the Lewis structure for phosphorus trifluoride. Let's do one which has multiple bonds, and configuration can be expressed as an example to show something with respect to bonding that has more than a single bond. So if we take some example, like for instance, let's take a simple example. Let's take the example of nitrogen. A nitrogen gas, which is the major component of our atmosphere, is symbolically represented as N2 with subscript G for gas. Now the N2 means that the nitrogen, in this case, consists of 2 nitrogen atoms. Now the atoms are combined covalently, and that means that they're sharing electrons. Now nitrogen and phosphorus are in the same group, so the valence electrons for nitrogen are the same configuration as the valence electrons for phosphorus. If we look at this, then we could easily draw the nitrogen as follows. We pair of electrons and then 3 singles like this. So how do we get an octet around each nitrogen with 2 nitrogens forming a pair of atoms to yield a nitrogen molecule? Well, let's take a look at this and examine how we can set it up. Again, we draw the structure as we did before. Now, obviously, the spatial configuration here is simply a line between them. Now, what we're going to do is we're going to create a single bond between these 2 nitrogens first. So in the second step, we might say, okay, so here we have a pair of electrons that are shared here. So we still have a pair here, a pair here. And obviously we have a lone one and a lone one in both cases here. So if we counted the number of electrons here, we'd have 1, 2, 3, 4, 5. So we have 10 electrons total. Okay, so now we've put them in space, we've counted the total number of electrons, and now we've made a single bond between 2 of them. Now you notice that they don't have octets. But in order to make octets, you may recall that we need to share electrons. And you can see that if we have 2 more electrons on each side of this, we could put together 2 more bonds. If we do this, in other words, we can move any of these to make pairs. So for example, we might take another step and say, okay, well, here's another configuration. We'll put 1, 2, 3, 4 nitrogen here, and we'll put this one here and this one here. And now we have a double bond between them, and you can see we still have 2 electrons left over. Well, we can use those 2 to make another bond. So we could say, all right, nitrogen, 1, 2, 3, 4, 5, 6, which represents a triple bond. We're going to move these electrons from the top to the outside because electron pairs tend to move away from each other if they can. So now we have nitrogen as a triple bonded structure with 2 sets of atoms. And so the structure might be more casually represented like this. So now we have a multiple bond of N2. The triple bond is very strong, and that's one of the reasons why nitrogen is such a stable structure in the atmosphere. And in order to get nitrogen to react, you have to first disrupt that triple bond, which makes